Hello, everybody. In this lecture, we begin a new topic. Actually, it is topic number 4 in the second part of this course, carrier transport in semiconductors. We will explore how the charge carriers, electrons, and holes respond to an external electric field, but also to an external magnetic field a little bit, and also how they behave in the presence of the non-uniformity of their own concentration. So in this lecture, but that will be in the next lecture, Einstein relation. So in this lecture, I will introduce the fundamental concepts from the theory of electric current. I will introduce the concept of current density, drift. I will derive the conductivity and resistivity of a semiconductor. I will comment on their temperature dependence and their dependence on the concentration of charged impurities. And finally, I will tell you how Hall effect devices work. Hall effect devices allow measuring experimentally, determining the sign and the concentration of the majority carriers in a semiconductor. So I give you a semiconductor, you perform this Hall effect measurement, and you tell me, this is a p-type semiconductor, and it has 3.21 10 to the 17th holes per cubic centimeter. All right, so let's begin. As a matter of fact, I'm not you probably know the stuff which will be presented in this slide. You have taken general physics course, but okay, let's review this material. So the two main reasons for transport of charge carriers in semiconductors that we will consider in these two lectures are drift and diffusion. Drift refers to the motion of charge carriers, directed motion, regular motion, in the presence of an electric field. Superimposed on this drift motion is the thermal motion of charge carriers, where electrons or holes as well, move in random directions with random velocities. They undergo collisions with the crystal lattice, with the vibrations with the phonons in the crystal lattice, and with the impurity atoms, defects, and so on in the crystal lattice. So this is the thermal motion. And thermal motion is fast, but on average, charge carriers that perform thermal motion do not go anywhere. So, because they are in thermal equilibrium and there is no transport in thermal equilibrium. Now, diffusion happens. Diffusion is basically thermal motion itself. So on average, a given charge carrier may get displaced due to thermal motion, and it gets displaced on average, after some time t, it gets displaced in a random direction by a random amount. And the well-known law of diffusion, that the average mean squared deviation of the position of a particle from the original position scales as time, as the first power of time. This is diffusion. Now, if you create somehow, for example, by non-uniform doping of charge carrier of donors or acceptors, non-uniform doping, you create a non-uniform distribution of charge carriers in space. So you have a little bit more charge carriers here than there. Then on average, the charge carriers will tend to diffuse from the regions where their concentration is high to the regions where their concentration is low. Oh, this is diffusion. Or maybe you inject charge carriers at some point, at some contact point into the semiconductor. Diffusion can be observed, of course, in everyday life. If you I do not open a bottle with perfumes somewhere, then perfume molecules will diffuse, spread out in space. So that's diffusion as well. All right, so now let us introduce the concept of uh, flux density, current density, and the related concepts. So the flux density can be understood as follows. You can talk about the flux density of anything. You can talk about the particle flux density, about the energy flux density, about the momentum flux density, a particular momentum component flux density, charge flux density, and so forth. So what is flux? Flux density. It is a number that tells you how much of a particular property, again, be it the number of particles, be it energy, be it charge, be it momentum, and so forth. So how much of a particular property is transferred per unit time through a unit surface area oriented, that unit surface area, that surface is oriented in the direct perpendicular to the direction of transfer of that property. So particle flux density, or particle current density, that's another name, tells you how many particles get transferred per unit time through a unit surface area oriented perpendicular to the direction of the particle flow. So in this way, particle current density or particle flux density is defined. We will be using the letter lowercase j for particle current density, also known as the flux density, and we will supply that letter with the subscript E or H for electrons and holes. Now, the current density is defined in a similar manner. How much charge gets transferred per unit time through a unit surface area oriented perpendicular to the direction of the charge transfer. So on average, your particles are moving in all random directions. If there is no drift, the particles are moving in random directions, and so the particle current density, the charge the electric current density, the flux density of the particles is zero. But if you apply an electric field, then there will be a preferred direction of charge transfer for electrons. The electrons are transferred opposite to the electric field. Holes, positively charged particles, are transferred in the direction of the electric field. So you need to orient your unit area perpendicular to the electric field, which is perpendicular to the direction of the average particle flow. Now, to relate the electric current density to the flux density of the particles, you simply need to multiply the flux density with the particle charge, which is the negative elementary charge for electrons and positive elementary charge for holes. So this is the electron current density. This is the hole current density. And we will be using the letter capital J for the current density, electric property. So uppercase J for electric current density, lowercase j for the flux density. We will be using both in this course. Okay, now let us think about the current density microscopically. So let's say that your electrons are moving. Let's talk about electrons. Your electrons are moving with the average velocity VE. Now, superimposed on this average velocity is the random velocity, so each electron is performing this crazy motion, but this crazy motion is on average results in the transfer in a particular direction. Let's call it the x direction. And because the particles if the particles perform only the thermal motion, then they have zero current density. We can ignore this random velocity component. We can focus just on the regular average velocity, which is assumed to be not zero because there is an electric field in the, so if the average velocity is in the positive x direction for electrons, then the electric field points in the negative x direction. All right, so how to relate the electron current density and the electron flux density to the average velocity of the electrons? For this, imagine a cylinder whose axis is aligned with the direction of electron motion, with the, that is the x-axis. So the two opposite bases of the cylinder are perpendicular to the x-axis. And let's call the area of the cylinder, the base area of the cylinder, A. And the length of the cylinder, let's call it V delta T, where V is the electron average velocity and delta T is some small time interval. After time delta T, all electrons that initially were inside the cylinder will get out of the cylinder through the, let's say, the right base, through this base. So we can now relate the number of particles, number of electrons that cross this area A, this cross-sectional area A, per unit time to the number of particles inside that cylinder. The number of electrons inside that cylinder is the product of the electron concentration, N, times the volume, which is the cross-sectional area A, times the length of the cylinder, V delta T. Ah, yes, here. And now, in order to get the electron flux density, we need to divide the number of electrons that cross the base A of the cylinder in time delta T. We need to divide it by the base area A and by the time delta T, because again, remind you, the flux density of particles is how many particles cross a unit area, hence you need to divide by the area, per unit time, hence you need to divide by the time delta T. And once you do this, of course, the area and area cancel out, the time delta T and time delta T cancel out in the numerator and in the denominator, so you get a very simple expression for the electron flux density. It is the product of the electron concentration times the average velocity of the electrons. And in principle, this expression makes perfect physical sense, because if you double the concentration of electrons, then you double the number of electrons that cross any area per unit time. If you double the velocity of the electrons, then you double also the number of crossings per unit time. So the particle current density must increase with the concentration of electrons and their velocity. And you can apply dimensional analysis to find the only correct combination of N and V, which has the dimension of the flux density. The flux density is measured in inverse squared centimeter times inverse second. So 1 over centimeter squared times second. 1 over centimeter squared times second. So concentration of electrons is measured in centimeters to the -3. Velocity is measured in centimeters per second. The product is measured in centimeters to the -2, seconds to the -1. So this is the only correct, dimensionally correct combination. As for holes, same treatment. You only need to replace the electron concentration N with hole concentration P, electron average velocity V sub E for electrons, with the hole average velocity V sub H for holes. All right, so now let's talk about the drift of electrons. As I said, I am talking about electrons, but same applies to holes as well. It's just for the sake of concreteness. So let's say your electric field is acting in the x direction. Electrons and holes, as I mentioned, as I said earlier, they perform very fast thermal motion. So the thermal velocity of an electron is in the range of tens of kilometers per second. So those electrons move very quickly with the velocities of the order of kilometers per second, and superimposed on this random thermal motion is the drift in the direction opposite to the electric field for electrons, because electrons are negatively charged. Every now and then, so the electrons move as wave packets. A wave packet is a linear combination of block states near the bottom of the conduction band, and those states have close values of the quasi-momentum. So altogether, when you create such a wave packet, it behaves as a particle. And so electrons behave as wave packets. We can apply a particle picture to understand the motion of the electrons. And every now and then, those electron wave packets collide with the crystal lattice. Now, more precisely, they collide with the phonons in the crystal lattice, and also with various defects and impurity atoms of the crystal lattice. So there are several collision mechanisms. All right. So these collisions explain a counterintuitive fact that when a charged particle finds itself in the presence of an electric field, the charged particle gets accelerated. If the charged particle gets accelerated, its velocity constantly increases. So without those collisions, if you think about electrons classically, you apply electric field, the current in the material would be constantly increasing, which is never observed in reality. The current assumes a steady value. It is not constantly increasing. Why is that? Because of those collisions. Between two collisions, an electron acquires a certain non-zero regular velocity component in the direction opposite to the electric field. So it is accelerated by the electric field, it acquires, but then when it collides with the lattice, its velocity is reset to zero. So the acceleration of the electron is the force divided by the electron mass. The acceleration of the hole is the force divided by the hole effective mass, and we should be using the conductivity effective masses. So hence the subscript conductivity. So force on the electron is negative elementary charge times the electric field. For holes, it is positive elementary charge times the electric field. So these are accelerations for electrons and holes. The electrons and holes are accelerated in the direction opposite to the electric field, electrons, and along the electric field, holes. And that acceleration stage has finite duration. Let's call the duration of this acceleration stage the collision time. So, and in fact, there is no reason to assume that electrons and holes have the same collision time. They typically don't. So we distinguish between the electron collision time, tau e, and hole collision time, tau h. Every time a collision happens, that extra velocity acquired by the charge carrier from the electric field is reset to zero. And then, so this is the collision. And then a new acceleration phase begins. The charge carrier gets accelerated, and then boom, collision, velocity is reset to zero. So this is how this drift process happens. Now, The average drift velocity can be estimated as the product of acceleration of the charge carrier times the collision time. That's your average velocity. Now, if you plug in the acceleration as the force, which is the charge times electric field divided by the effective mass, then you find that the average velocity is proportional to the electric field. And the proportionality constant is called the mobility. It is denoted with the letter mu, usually. Electrons' average velocity is against the electric field, so it is negative. Electron mobility times the electric field. Electron mobility is elementary charge times the collision time, tau, divided by the effective mass. That's the mobility. And the similar expression is valid for holes. Hole mobility is elementary charge, hole collision time, divided by the hole conductivity effective mass. So now we have understood why electrons do not get accelerated constantly because of the collisions. We have expressed the drift velocity of the electrons and holes in terms of their mobilities. And one final remark, if you plug in the numbers, like reasonable numbers, for example, electric field is, I do not know, set electric field to 100 volts per centimeter, for example, the typical collision time has the value of maybe picoseconds, so it is fairly small, maybe hundreds of picoseconds. You can try the effective mass to be set to be the same as the free electron mass, that is 9.1 10 to the negative 31st kilograms. Then you will quickly establish that the average drift velocity of your charge carriers is fairly tiny. It is in something like centimeter per second range. It is many orders of magnitude smaller than the than the thermal velocity of your charge carriers, which is in the kilometers per second range. So many orders of magnitude difference between the drift velocity, which is tiny, of the order of centimeters per second, and the thermal velocity, which is huge, of the order of kilometers, or tens of kilometers per second, maybe even 100 kilometers per second. All right. So now that we have the drift velocities, let us use that expression. Let us use our drift velocity to get the particle flux densities or particle current densities due to drift. The particle current density or the flux density is the average velocity times concentration. The average velocity is mobility times the electric field, with either the minus sign or the plus sign for electrons and holes. So these are the drift flux densities for electrons, negative electron mobility times electron concentration times the electric field, and for holes, hole mobility times hole concentration P times the electric field E. Notice that the signs are opposite to each other. And now to get the electric current density, we need to multiply the particle current density with the particle charge. And here is a mistake in the electron electric current density. And now there is no mistake. So the sign here, the product of the electron charge negative E times the electron flux density should give me a positive number. Minus times minus gives me a plus. Luckily, I can press the pause recording button and fix this small typo. So notice that electric current density for electrons and for holes have the same sign, because the electric current density is the direction of the electric current is taken by convention to be the same as the direction of motion of positive charges and opposite to the direction of transfer of negative charges. So, all right. Now, conductivity and resistivity. We add up the electric current densities due to electrons and due to holes, add them up together. We will get the net, the total current density due to both charge carriers. It is proportional to the electric field. The proportionality constant, sigma, is called the conductivity of the material, and it is given by this expression, elementary charge times the sum of electric mobility times electron mobility times electron concentration plus hole mobility plus hole concentration. The inverse of the conductivity is the resistivity. 1 over sigma is the resistivity. In the absence of generation processes and for low injection level, we can replace the non-equilibrium concentrations of electrons and hole with their equilibrium values, N naught and P naught. All right, so now we can relate the electric current density to the properties of the material. We know what the conductivity, resistivity is. Now, what about the current? Let's say you have a semiconducting bar, or in fact, it could be any conductor, could be a semiconductor. Current density tells you how much charge is transferred through a unit surface area per unit time. Current tells you how much charge is transferred through the whole thing per unit time. So to relate the current density to the electric current, you simply need to multiply the current density with the cross-sectional area of your conducting or semiconducting bar. So A is the cross-sectional area, so I is the current, I equals A times J. The current density is conductivity sigma times the electric field that exists inside the material. And the electric field is the ratio of the voltage across the material, V, to the length of the material, L, so V over L. And so we see that the current is proportional to voltage. This is Ohm's law, famous Ohm's law, which tells you that current through a material is, through a conducting object, is the ratio of voltage across the ends of the conductor to the resistance of the conductor, R. The resistance is resistivity times the length divided by the cross-sectional area, as follows from the simple formulas. The inverse resistance is called the conductance. Resistance is measured in ohms. Conductance is conductivity sigma times cross-sectional area divided by the length. Conductance is measured in Siemens. Siemens is inverse ohm. Now, the central parameter which determines the conductivity, the resistivity, and hence the conductance and the resistance of a material is the mobility of charge carriers. And mobility, in turn, is proportional to the collision time. And hence it is inversely proportional to the frequency of collisions of a given charge carrier, electron or hole, with the crystal lattice. Now the frequency, what does those charge carriers collide with? And now I am repeating this maybe for the third time in this lecture. The collisions are primarily with the phonons, the quanta of lattice vibrations, and also with various defects and impurities in the crystal lattice. Let's say the crystal lattice is defect-free. Then the frequency of these collisions is proportional to the total number of impurities, that is, donors and acceptors, in a unit volume. So the concentration of donors plus the concentration of acceptors. And it also should be proportional to the temperature raised to some power. So it is not a direct proportionality. The frequency of collisions increases with temperature, but not as the first power of temperature. In silicon, empirically, we know that the frequency of collisions increases with temperature as t to the power 2.2 or 2.3, depending on what kind of charge carriers these are, electrons or holes. So these plots show the mobility of electrons and holes in silicon as a function of temperature for different doping levels. And this plot shows the mobility as a function of the impurity in silicon, again, as a function of the concentration of impurities, donors and acceptors, and donor plus an acceptor, at the room temperature, 300 kelvins. So we see that mobility decreases with impurity concentration and it decreases with temperature. Why? Because the frequency of collisions increases both with impurity concentration and with the temperature. Now, the total frequency of collisions is the sum of collision frequency with the impurities plus the collision frequency with the phonons. So hence the inverse collision times add up. The frequencies add up, but the frequency is the inverse collision time. All right, so finally, the last slide in this lecture describes the Hall effect. Hall effect is a standard procedure to determine both the sign and the concentration of majority carriers. This is a typical situation when the concentration of, let's say, electrons, let's assume for definiteness that the semiconductor is of n-type, then typically the concentration of electrons is higher than the concentration of holes by at least several orders of magnitude. So holes can be neglected. Hole contribution to the total conductivity can be neglected in an n-type semiconductor. And of course, electrons can be neglected in a p-type semiconductor. So let's say that your semiconductor is of n-type. And this is the schematics of the experimental setup. You take your semiconductor bar, you apply voltage between the two ends, this one and this one. The length of the bar is L, and let's say the width of the bar is W, and the thickness of the bar is D. So you apply a voltage in the positive x direction, so the current flows in the positive x direction, and you also apply a magnetic field B in the direction perpendicular to the plane of the bar, that is, in the direction perpendicular to the flow of the charges. Since we assumed that the semiconductor is of n-type, the majority carriers are electrons and they flow from right to left, so from this end of the bar to this end of the bar, in this direction opposite to the polarity of the voltage. When a charge is moving with some velocity, with the drift velocity, in the presence of the magnetic field, it feels the Lorentz force or the magnetic force, which is given by this expression here, product of charge times the cross product of the charge velocity vector and the magnetic field. Now, if the electrons are moving to the left, in this diagram, to the left, the magnetic field points up. The direction of this Lorentz force or magnetic force on the electrons can be established using the right-hand rule, in which you align your index finger of your right hand with the direction of the charge motion. The middle finger will be pointing, will be aligned with the direction of the magnetic field. It will be up. And then the thumb shows the direction of the cross product, V cross B. But the force is the product of charge and this cross product V cross B. And the charge of the electron is negative. So the force on the electron will be pointing opposite to where the thumb of your right hand is pointing. That is, the force points out of plane of the figure. This means that the electrons will feel a force out of plane of the figure, and as a result, they will drift slightly out of plane of the figure, that is, toward that side of the semiconductor bar, which is closer to us. This side will be charging up negatively. The opposite side will be depleted of electrons. It will charge up positively. As a result, a voltage will develop in the direction between these two sides, this one and this one, in the direction perpendicular to the flow of the current and the magnetic field B. Now, if your charge carriers, and the polarity of that voltage, this side, which is closer to us, is negative, and this side is positive. Now, if your charge carriers were holes, the majority carriers were holes, then the polarity of this voltage would be reversed, because holes, if these were holes, then they would be drifting to the right. The direction of the magnetic field points up, and the force on the holes, if this were a p-type semiconductor, the force on the holes would be still pointing toward us. So this side, which is closer to us, would be positively charged. So from the polarity, now you can measure the voltage that develops between these two sides, this one and this one, and the polarity of that voltage tells you what the majority carriers are, electrons or holes. Now we can also determine the concentration of the majority carriers, and this is how it goes. So this magnetic force pushes the majority carriers in the direction out of plane of the figure, toward us. As a result, this side becomes charged and the opposite side becomes charged. This results in an electric field, in the Hall electric field. The Hall effective field can be, and this Hall effective field is directed so as to prevent further charging up of these two opposite sides, this one and this one. So eventually the charging up of these sides will stop, because the effect of the electric force due to the Hall electric field will perfectly balance the effect of the magnetic Lorentz force on the majority carriers. Now let us figure out this Hall electric field. The electric force is the ratio of Hall voltage to the width of the semiconductor bar. And so this is the Hall electric field, V Hall voltage to the width. Multiply this with the sign of the majority carriers, Q, be it electrons or holes, doesn't matter. That gives you the force on the majority carriers due to the Hall electric field. It must be balanced by the magnetic force. Charge times the drift velocity times the magnetic field gives you the magnitude of the magnetic force. Now, of course, charge and charge can mutually cancel in this relation, and we find that the Hall voltage is width of the bar times the drift velocity times the magnetic field. But the drift velocity can be related to the electric current through the bar, which is the product of the bar cross-sectional area, width times thickness, W times D, times the electric current density. Electric current density is charge times the concentration of charge carriers, assumed to be electrons here, n, times the drift velocity d. So the drift velocity is expressible in terms of the electric current. As a result, we find the relation for the Hall voltage. It is given by the product of the electric current through the bar times the magnetic field divided by the thickness, concentration of charge carriers, and elementary charge. So this is the magnitude of Hall voltage. If the majority carriers are holes, then replace N with P. Now, Hall effect was discovered around the year 1880. Maybe it was a little bit earlier, but I do not remember exactly, by Edwin Hall from Johns Hopkins University. The remarkable thing about this was that it was discovered before electrons were discovered. So people didn't know, people could measure the current. So that it was about the time when Maxwell formulated his equations, his famous equations for the electric field, but people were not aware that the charge carriers, electrons, exist, because it was way before, about 20 years before, maybe 10 years or 15 years, 15 years before Thomson discovered electrons. So there was no theory of Hall effect. Another remarkable thing was that Edwin Hall, at the time of discovery, was 24 years old. He was such a brilliant young man. And what was going on in his head? Why would he want to take, let's say, a golden or whatever copper bar? Maybe, I think it was a golden bar, was golden foil. Apply voltage in one direction, apply magnetic field in the opposite, in the perpendicular direction, and measure the voltage in the direction perpendicular to the applied voltage and the magnetic field. It's beyond me. It's a mystery, but it was a brilliant. Maybe this discovery has been made by accident. But nowadays, it is a standard technique to find out what charge carriers are dominant in your semiconductor and what the concentration of the majority carriers is. Of course, you can develop the theory of Hall, generalize the theory of Hall voltage to the case when both electrons and holes are present. And I invite you to investigate that question on your own. For now, thank you all very much for your kind attention, and I'll see you in the next lecture. Goodbye.